Just in case you started watching this video in the hope of looking at something that is really improper, let me clear any doubts. No, we're going to do very proper things. In fact, improper integrals is a very proper method of integration. Okay? What the word refers to is the fact that we're going to be trying to resolve a situation where an integral shouldn't really be computed because of our original definition. But what we're going to do is we're going to realize that, well, in some situation it can still be computed. It makes sense to compute it, so we are going to give meaning to it. Let me be a little bit more concrete. Okay, so remember what a definite integral is, right? Well, we defined it as the limit as n goes to infinity of the sum, etc., etc. But it's basically the integral from a to b of a function f of x dx. This is also what we call the Riemann integral, and we know that we can compute it. Not always, but we can compute it under very mild assumptions. Okay? In fact, just about the only things that we have required in order to be able to compute this integral are, first of all, the two limits should actually be real numbers. Okay? So a has to be a number, b has to be a number, and the other thing is that f of x has to be a continuous function. Okay? Well, what happens if in fact one of these conditions is false? So either a or b are not numbers, or the function is not continuous. Let me give you a very simple example to illustrate why we will be interested in doing something like this. Consider this integral. Integral from 0 to 2 of sine x over x dx. Alright, looks fine and dandy except for the fact that we can't really compute it because this function is not continuous at 0. It has a discontinuity at 0. But if we interpret this integral as the area under the curve, it turns out that this is the area under the curve of the function sine x over x, which looks like that. Well, where is the discontinuity? If you remember from our work in the fall, the discontinuity of sine x over x is only at the point 0, 1, and it's a single point hole, right? Yeah, but the area of that region still exists. All we're missing is a single point, which does not add anything to the area of the region. So we would like to be able to compute that integral, except that we cannot, at least not based on the fundamental theorem, because that only works if the function is continuous. So how are we going to do it? Well, here is how.